The kænḍɛlə is the SI base unit of luminous intensity, that is, luminous power per unit solid angle emitted by a point light source in a particular direction. Luminous intensity is analogous to radiant intensity, but instead of simply adding up the contributions of every wavelength of light in the source's spectrum, the contribution of each wavelength is weighted by the standard luminosity function. A common candle emits light with a luminous intensity of roughly 1 kænḍɛlə. If emission in some directions is blocked by an opaque barrier, the emission would still be approximately 1 kænḍɛlə in the directions that are not obscured. The word kænḍɛlə means candle in Latin. Definition: like most other SI base units, the kænḍɛlə has an operational definition. It is defined by a description of a physical process that will produce 1 kænḍɛlə of luminous intensity. Since the 16th General Conference on Weights and Measures in 1979, the kænḍɛlə has been defined as the kænḍɛlə is the luminous intensity, in a given direction, of a source that emits monochromatic radiation of frequency 540 times 1012 Hz and that has a radiant intensity in that direction of 1/683 watt per steradian. The definition describes how to produce a light source that emits 1 kænḍɛlə. Such a source could then be used to calibrate instruments designed to measure luminous intensity. The kænḍɛlə is sometimes still called by the old name candle, such as in-foot candle, and the modern definition of candle power. Explanation: the frequency chosen is in the visible spectrum near green, corresponding to a wavelength of about 555 nanometers. The human eye is most sensitive to this frequency, when adapted for bright conditions. At other frequencies, more radiant intensity is required to achieve the same luminous intensity. According to the frequency response of the human eye, the luminous intensity for light of a particular wavelength lambda is given by where IV is the luminous intensity in kænḍɛlės, i.e. is the radiant intensity, and with senior n is the standard luminosity function. If more than one wavelength is present, one must sum or integrate over the spectrum of wavelengths present to get the total luminous intensity. Examples: a common candle emits light with roughly 1 kænḍɛlə luminous intensity. A 25W compact fluorescent light bulb puts out around 1700 lumens. If that light is radiated equally in all directions, it will have an intensity of around 135 kænḍɛlės. Focused into a 20 degrees beam, it will have an intensity of around 18,000 kænḍɛlės. The luminous intensity of light-emitting diodes is measured in millikænḍɛlės, or thousandths of a kænḍɛlə. Indicator LEDs are typically in the 50 millikænḍɛlės range. Ultra-bright LEDs can reach 15,000 millikænḍɛlės, or higher. Origin: prior to 1948, various standards for luminous intensity were in use in a number of countries. These were typically based on the brightness of the flame from a standard candle of defined composition, or the brightness of an incandescent filament of specific design. One of the best known of these was the English standard of candle power. 1 candle power was the light produced by a pure spermaceti candle weighing 1/6 of a pound and burning at a rate of 120 grains per hour. Germany, Austria and Scandinavia used the Hefner Kerze, a unit based on the output of a Hefner lamp. It became clear that a better defined unit was needed. The Commission Internationale de l'Éclairage and the CIPM proposed a new candle, based on the luminance of a Planck radiator at the temperature of freezing platinum. The value of the new unit was chosen to make it similar to the earlier unit candle power. The decision was promulgated by the CIPM in 1946. The value of the new candle is such that the brightness of the full radiator at the temperature of solidification of platinum is 60 new candles per square centimeter. It was then ratified in 1948 by the 9th CGPM, which adopted a new name for this unit, the kænḍɛlə. In 1967, the 13th CGPM removed the term new candle and gave an amended version of the kænḍɛlə definition. specifying the atmospheric pressure applied to the freezing platinum. The kænɗɛlə is the luminous intensity, in the perpendicular direction, of a surface of 1/600,000th square meter of a black body at the temperature of freezing platinum under a pressure of 101,325 newtons per square meter. In 1979, because of the difficulties in realizing a Planck radiator at high temperatures and the new possibilities offered by radiometry, the 16th CGPM adopted the modern definition of the kænɗɛlə. The arbitrary term was chosen so that the new definition would exactly match the old definition. Although the kænɗɛlə is now defined in terms of the second and the watt, the kænɗɛlə remains a base unit of the SI system. By definition, SI photometric light units, SI photometry quantities V, T, E, standards. Organizations recommend that photometric quantities be denoted with a suffix V, to avoid confusion with radiometric or photon quantities. For example, USA standard letter symbols for illuminating engineering USAS Z7.1-1967, Y10.18-1967. ABC alternative symbols sometimes seen. W for luminous energy, P or F for luminous flux, and Rho or K for luminous efficacy. ABC J. Here is the symbol for the dimension of luminous intensity, not the symbol for the unit joules. Relationships between luminous intensity, luminous flux, and illuminance. If a source emits a known luminous intensity IV in a well-defined cone, the total luminous flux phi-V in lumens is given by phi-V equals IV 2 pi 1 minus cos, where A is the radiation angle of the lamp, the full vertex angle of the emission cone. For example, a lamp that emits 590 candelas with a radiation angle of 40 degrees emits about 224 lumens. CMR 16 for emission angles of some common lamps. If the source emits light uniformly in all directions, the flux can be found by multiplying the intensity by 4 pi. A uniform 1 kænɗɛlə source emits 12.6 lumens. For the purpose of measuring illumination, the kænɗɛlə is not a practical unit, as it only applies to idealized point light sources, each approximated by a source small compared to the distance from which its luminous radiation is measured, also assuming that it is done so in the absence of other light sources. What gets directly measured by a light meter is incident light on a sensor of finite area, i.e., illuminance in lumen per square meter. However, if designing illumination from many point light sources, like light bulbs, of known approximate omnidirectionally uniform intensities, the contributions to illuminance from incoherent light being additive, it is mathematically estimated as follows.